Good morning, year fives. Today we're gonna, we ended off with the key assumptions for kinetic theory, the last lesson. So today we're gonna move on to some derivation of equations. Now, the last lesson I also told you to read textbook page 107 to 109. Now, if you haven't already read the textbook, can you please pause here and go and read those pages first? Because if you continue doing watching the video, you will not be able to understand what I'm saying unless you have read the textbook. So the last lesson previously we've already mentioned about that pressure equals to force over area. The number of moles is equals to number of particles over Avogadro's constant. We've also learned that PV equals to nRT. So today we're gonna learn how to derive kinetic energy. Ke is our kinetic energy equals to 3/2 kBT. So for today's lesson, this is what we're going to be deriving, these three equations, and ultimately show that kinetic energy is proportional to temperature. Now, do you notice that this equation looks very similar to this? Only difference is that it has an n here. So the equation that is given in your data booklet, this would be for one molecule. Okay, so this is the kinetic energy for one molecule, whereas what we will be deriving will be for all molecules. So this is the Ke for all the molecules. Okay, so let's start. Now, assuming we have a cube of length L, so say this is all L. Okay, sorry, it doesn't really look like a cube, but we just imagine that's a cube. And I have a gas particle in it. My gas particle of mass m is moving to the right with velocity v. Now, it moves to the right, hits the wall, and comes back with the same speed because this is an ideal gas. So what is its velocity going to be? So I'm going to take velocity equals to, before we continue, let's draw it out first. So we have this cube of length L, this particle mass m moving to the right with v. It's going to hit the wall and come back with a velocity of negative v, if I take to the right as positive. Okay, so the speed would be 2L over t, because distance over time, right? The distance to go there and come back would be 2L, and the time taken would be t. Now, what is the force on one molecule by the wall? So in order to find that force, I'll use F equals to ma. The mass of the molecule would be m. What's the velocity? What's the acceleration of the particle? V minus u over t. What is its final velocity? Final velocity is minus v. What's the initial velocity? Positive v over time taken. So you end up getting minus 2mv over t. So this is the force on one molecule by the wall. Now, look at the top equation. I'm going to leave 1 over t on the right hand side. I'm going to bring 2l over, so I get v over 2l. Now, if this is called equation 1 and this is equation 2, I'm going to substitute equation 1 into equation 2. Equation 2, you can see, is actually 2mv times 1 over t, right? So when I substitute 1 over t in with v over 2l, you end up getting minus 2 the 2 and the 2 will cancel each other away. So we end up getting minus mv squared over L. So this is the force on one molecule by the wall. Now, what if I want to find the force on the wall by one molecule? According to Newton's third law, every action is an equal and opposite reaction. So the force on the wall will be the same as the force on the molecule, right? Just that the direction is different, so it'll be mv squared over L. So we go to the next page, let's copy that down again. Force on wall by one molecule. Now this is in one direction, right? We only talk about the horizontal direction, so we call that the x direction. And that force is mv squared over L. So what's the total force on the wall by n number of molecules in the x direction? Total force on the wall by n molecules in the x direction. So I'm going to call that Fx total, okay, because it's only in the x direction. So if this is mv squared over L is the force by one molecule. If I've got two molecules, then I'll have to add them up, right? mv squared over L plus mv squared over L. Three molecules, I add mv squared over L plus times 3. So what am I doing? Basically, if I have n molecules, it will be m over L. Now, but each molecule have got different velocities. So say the first one has got velocity v1. So be v1 square plus v2 square plus v3 square all the way until vn square. Right? Now, if I have v1 square plus v2 square plus v3 square all the way until vn square, when I add them up, plus vn square, this is the total square velocities, right? Square of the velocities. If I want to find the average, what do? I will divide it all by n. Now, I'm going to call this cx square with a line above. What does this mean? This means cx square with a line above is called the mean square value of velocity. And in this case here, it's in the x direction. Okay, it's our average square velocity in the x direction. Now, do you notice that if I bring my divide by n over, so I get v1 square plus v2 square plus all the way until vn square equals to ncx square. Left hand side here is the same as this part here. So I'm going to substitute that inside. So I get m over L times ncx square. Now, this is the total force on the wall by n number of molecules in the x direction. If I had done this in the y direction or in the z direction, the total force in each direction will be the same, right? So this tells us that the mean square velocity in the x direction will be the same as the mean square velocity in the y direction, which will be the same as the mean square velocity in the z direction. And how do I find the mean square velocity, the total mean square velocity in all directions? The total mean square velocity in all directions, I will add them up. Hence, since we say that they are all the same, this is actually the same as 3 times of the mean square velocity in the x direction, which is equal to the total mean square velocity. And so if I want to just find the mean square velocity in the x direction, it is actually 1/3 of the mean square velocity in all directions. So if I were to substitute that into my F total, what do I get? Fx total, my total force in the x direction. I'll get m over L n times 1/3 c square. So we end up getting 1/3 n m over L times c square. Okay, so this is the total force in the x direction in terms of the total mean square velocity. So if I want to find the pressure acting on one surface, pressure in the x direction is equals to force in x direction divided by the surface, right? So let me draw that out. Since my particle is moving to the right, that is the direction, isn't it? So what's the surface? The first surface that we're talking about is this surface over here. So what's our Fx again? It'll be 1/3 nm over Lc square. And then I need to divide it by the surface area A. What is surface area A? surface area A is actually L times L, isn't it? So it's L square. So I end up getting 1/3 nm over L c square times 1 over L square. So I get 1/3 nm over L cube times c square. What is L cube? Length times breadth times height is our volume, right? So you get 1/3 nm over volume c square. Okay, so what does this equation actually mean? What does N stand for? N stands for number of molecules or number of particles, right? Number of molecules. What is M, small m? Just now we said that small m is the mass of one molecule. So if I have number of molecules multiplied by the mass of one molecule, what does that actually give us? That gives us a total mass. Total mass of all molecules. Right? That would be big N times small n. Now I'm going to use capital M to represent this. So I get 1/3 m over v times c square. What's mass over volume? Mass of all the particles divided by volume that it takes up. Mass over volume, what does it sound like? Remember we said density equals to mass over volume. So this actually equals to 1/3 density c square. So this is the first equation that you were supposed to derive, isn't it? So this is, now please take note, this is pressure in the x direction. But since pressure in a fluid acts in all directions equally, pressure in the x direction will be the same as pressure in the y direction, which will be the same as pressure in the z direction. So the total pressure will just be 1/3 rho c square. Alright, so this is pressure in all directions. Now if I go back to the previous equation of P equals to 1/3 nm over volume times c square. Now if I come back to this equation over here, and I bring my V over to the left hand side, so I get PV equals to 1/3 nm c square. Then I multiply 3 over 2 on both sides. So 3 over 2 PV equals to 3 over 2 times 1/3 nm c square. The 3 will cancel with each other. So I get 3 over 2 PV equals to half nm c square. And then remember just now we said that number of particles times mass of one particle is equals to total mass, right? So that gives us half mc square. What's half mc square? Remember c is mean square speed, right? Mean square speed, which is like speed or velocity. Half mv square. What does that remind us of? Kinetic energy, isn't it? So this is our kinetic energy of all particles, because we're talking about more than one particle, of all particles. Alright, so we have kinetic energy of all particles equals to 3 over 2 PV. Now, if we recall, PV equals to nRT, or you can say PV equals to nKT, right? Now I'm going to use PV equals to nKT, alright? And using this, PV equals to nKT, I multiply 3 over 2 on both sides. So what do we get? Notice that now left hand side 3 over 2 PV. Over here also 3 over 2 PV is the same, right? Which means that the right hand side are technically equal to each other. So I have half mc square equals to 3 over 2 nKT. Half mv square is our kinetic energy. 3 over 2, n is the number of particles, k is a constant, Boltzmann constant. So these are all constants. Can you see that your Ke is then proportional to your temperature? So using this last few slides, it's to show us that Ke, kinetic energy in an ideal gas, is proportional to temperature only. Doesn't matter, the kinetic energy is not affected by the the state that it's in. All right. So with this done, now let's pause here. Before I continue, I would like all of you to, if you have actually watched the video, I would like you to send me an email to tell me what is one thing you're going to do when the circuit breaker period ends. What's one thing that you're looking forward to doing when circuit breaker ends? And those of you who emailed me your answer, you'll get 2 extra marks for your next graded assignment. All right, so let's pause here and do example 3. Then you unpause it when you're done. Okay, so for example 3, what did they ask us to do? They tell us that the temperature of a fixed mass of an ideal gas changes from 200 degrees Celsius to 400 degrees Celsius. They asked us for the ratio for the mean KE at 200 degrees to the mean KE of the gas at 400 degrees Celsius. So the last slide, what did we just learn? We just learned that KE is proportional to temperature, isn't it? So if I want to find KE at 200 degrees Celsius to the KE at 400 degrees Celsius, some of you might just have done this. 200 over 400, okay, equals to half. So you chose answer A. Now answer is B, not A. So what's wrong? Why is the answer not half? Remember what did we say about temperature? In the last lesson, I mentioned something about temperature. I kept emphasizing temperature in ideal gas. What unit must you use? You must use kelvins. That's right. So you need to convert your degrees Celsius to kelvins. Now how to convert? 0 degrees Celsius equals to how many kelvins? Equals to 273 Kelvin. So if I have 200 degrees Celsius, it'll be 200 plus 273 to get us in kelvins. So what do? 200 plus 273 divided by 400 plus 273. That will give us 473 over 673. Now because it's MCQ, you cannot use your calculator. So you need to approximate it. So it will be about 500 to 700. Cancel away the zeros, you get 5 over 7. Like you know that 5 over 7 is definitely less than 1. So C and D will be out. And since it's definitely not half or so best answer will be B. Pause here and try example 5. Alright, for this question, let's highlight what's important first. They tell us that we have length L with cross-sectional area A. It contains n number of molecules and is at temperature T. The question asks us for the force acting on the area of the cylinder marked A due to the gas. So basically we want to find out what is the force in this direction here. So what do? How do we do that? You start off with pressure equals to force over area. So force would be pressure times area. Now how do we find the pressure then? Since you know N, you know T, what else can we find? What formula do we use? We use PV equals to nRT or PV equals to nKT. Which one do we use? Now I will not use the first one because they did not, in the question they didn't give me number of moles. Whereas in the question they gave me the number of particles. So I will use PV equals to nKT. Now if I have PV equals to nKT, what is P equals to? P is equals to nKT over V. What's the volume in this question? The volume of the cylinder, it will be A times L, right? So let me substitute that in. nKT over AL times A. So you can cancel away your A, you're left with nKT over L. So answer is D. Now sometimes I'll write K. K is the same as KB, alright? Boltzmann constant. Again, pause here and try this out on your own. So if you have already done it, you can check. A and C requires you to prove or to show, so that one, the answer is already given. B, D, and E, check your answers if these are correct. Now, if you got it right, you can skip this part. If you don't understand, let's go through it together. So they gave us the volume, they gave us the pressure, they gave us the temperature. Always label what is given. Volume, pressure, temperature. What else did they give us? They give us molar mass. They asked us to show that the mass of the helium atom is 6.6 times 10 to the power of minus 27 kg. So how do I show that? Now you need to know that what is molar mass? Previously we have learnt, right, that number of moles equals to mass over molar mass. Number of moles equals to mass over, mass over molar mass. Right, I told you small m over big M. What else do you know? If you look at your data booklet, you're also given that number of moles is equal to number of particles over Avogadro's constant. Right, so if you want to find what the mass is, M, it will be your molar mass times N over Na. What's our molar mass? 4. But notice the unit here is grams, unit here is in kg. So you need to convert your molar mass to kg. So it'll be 4 times 10 to the power of minus 3. What's N? They asked for the mass of a helium molecule. Please take note of that. So we're talking about one molecule. So that means our number of particles will be 1 over 6.02 times 10 to the power of minus 23. Sorry, not minus. Oops. Positive 23. So you type this into your calculator, you would be able to get 6.6445 times 10 to the power of minus 27 kg. So you can prove, or you can show that it becomes 6.6 times 10 to the power of minus 27 kg. Part B. They asked us to estimate the average speed of the helium atoms in the container. So if they ask us for speed, now which equation or which formula gives us speed? If we look at our data booklet for under topic 3.2, there's nothing that gives us speed, right? But it gave us energy, kinetic energy. And what's the formula for kinetic energy? Half mv squared. And over there you have your speed, isn't it? So you have your half mv squared kinetic energy is equals to 3 over 2 nkt. Now, the 2 on each side can cancel away. What's the mass? Now, they say mass of the helium atoms, right? What's the total mass of all the helium atoms? We have already learned or shown just now 6.6445 times 10 to the power of minus 27. V squared is unknown, times 3. Now, how many particles do we have? N. Do I know how many particles we have? I don't know, right? So how do I do this? Just now we did this. Number of moles equals to mass over molar mass, which is equals to number of particles over Avogadro's constant. Now, if I don't know what N is, N would then be Na times M over big M. Right? So let's fit that in. What's Na? 6.02 times 10 to the power of 23. What's the total mass? Oh, let me put it in terms of the equation. So I have mv squared equals to 3. What's N? Na M over big M times kT. I have mass on both sides, the total mass of the particles. So I'm left with V squared equals to 3 times of 6.02 times 10 to the power of 23 divided by big M, molar mass, which is 4 times 10 to the power of minus 3 times K. What's K? 1.38 times 10 to the power of minus 23. Please check your data booklet for this value. Temperature, 320. So you can find out what V is, which you will get 1412 meters per second. Now remember, all our values here are written to 2SF, so round it off to 2SF. 1.4 times 10 to the power of 3 meters per second. Moving on to C, they ask us to show that the number of helium atoms is about this. So basically right now I'm trying to look for a big N. Right, number of helium atoms. So how do I do that? We use PV equals to NKT. Since you know what P is 5.1 times 10 to the power of 5. What is V? 3.2 times 10 to the power of minus 6. N is unknown. K is 1.38 times 10 to the power of minus 23. And T is 320. So from here you can find out what N is, which will give you 3.6756 times 10 to the power of 20 atoms, right? So that will approximate it to 4 times 10 to the power of 20 atoms. Okay, done. Now, last part, D. Sorry, not last part. Second last part. They tell us that each helium atom has got this value. And I want to find the ratio of the total volume of helium atoms to the volume of helium gas. Now, what is the difference between helium atom and volume of helium atom and volume of helium gas? Now, volume of helium atom means if all my helium atoms are compressed together. Okay? Now, each atom has got this volume. Right? So if I have 2, 4, 6, 8, 10, 12. If I have 12 particles, I'll have to take this whole volume of each particle times 12. That is the volume of the helium atoms. But what about volume of helium gas? Now, you know that helium gas isn't neatly arranged, right? It's not stuck together. So I can have the same 12 atoms, but now they're all spread out because it's a gas. What's the volume of the gas then? It will be the volume of the container. Alright? So that's the difference. So how do I find the total? So volume of helium gas to volume of helium atoms to volume of helium gas. So how many atoms do we have? I know one atom has a volume of 4.9 times 10 to the power of minus 31. I need to multiply it by the total number of particles. What's the total number of particles? 3.6756. So 3.6756 times 10 to the power of 20. Then I divide it by the volume of helium gas. What's the volume of helium gas? They already told it to us. 3.2 times 10 to the power of minus 6. So calculate this out in your calculator. And you will get something like 6.125 times 10 to the power of minus 5. Right? So approximate it to SF 6.1 times 10 to the power of minus 5. So you can see that the ratio of the volume of helium atoms to the volume of helium gas is very small. Right? Which means that if I change the ratio, I change it to volume of helium gas to volume of helium atom, it will be very big. The space that the gas contains or takes up is a lot bigger than the amount of space that it actually needs. So this is where we come to part E. When they ask us to explain your answer in part D part 1 with reference to kinetic model, why this sample of helium can be assumed to be an ideal gas. Now, what did we say about the assumption of ideal gas? We said that for ideal gas, the volume of the particles must be negligible, right, compared to the volume of the container. So because of our calculation, the ratio that shows us that it's very small, we can say that, okay, this gas here is ideal. Alright, and we are done. So please complete all the worksheets that I have given to you and that I've told you to complete.